Hi everybody. We're going to pick up where we left off in chapter 5, which is on tides. So basically before Newton's work on gravity, nobody was really able to explain why we have tides. There were a couple of things known, and that was that the tides are caused by bulges in the surface of the Earth's ocean, and that there was two bulges, one on either side of the Earth. Also, the occurrence of the tides at a given location is due to the Earth's rotation. Centripetal acceleration toward the moon is the key to understanding tidal bulges. If you notice in this picture, you see a bulge on the top, and you also see a bulge showing on the bottom of this picture. Now, what we see here is high tides caused by the gravitational attraction of the moon and the Earth's spin. So notice right here we have a bulge on this side, and right here we have a bulge on this side. Okay, those are going to be the areas of our high tides. We have two types of tides. We have spring tides and we have neap tides. Spring tides are the highest tides. So the highest high tide, the highest low tide. Notice this top picture, your spring tides are only going to occur when you have a new moon or a full moon. Notice this orientation. You have the sun, the moon, and the earth all in one horizontal line. Neap tide, on the other hand, is going to be the lowest tides. Here, you're going to have the lowest high tides and the lowest low tides. Notice this orientation. You have the sun, and then you have the moon and the earth perpendicular to the sun. A neap tide is going to occur at a third quarter moon and also at a first quarter moon. Now, you also would expect to observe solar tides, tides that are due to the sun, because we know that sun also exerts a gravitational pull on the earth. The earth is basically falling toward the sun. They occur, but their heights are less than about 1/2 those due to the moon. So one reason is that the gravitational force on the earth is about 180 times as large as the moon. That's the sun's gravitational force. But your sun is also 400 times farther than the moon. So you don't see that effect as being as pronounced as the lunar effects. Now, if you look at law of gravitation, we've talked about it. Now, the law of gravitation is thoroughly tested within the solar system. We know we can use it to account for the planet's moons, irregularities during the mutual attraction of all the planets. But what about outside the solar system? Well, we haven't sent any probes outside the solar system, so we're not sure if it holds outside the solar system. We do have some stars in our galaxy that revolve around a companion star. These are what's known as binary star systems. So looking at binary star systems, they revolve around each other in exactly the way that is predicted by Newton's laws. So occasionally we might see a star that's moving in an elliptical path. Well, if we have faith in Newton's law, we know there's a companion star out there. It just might not be visible to us. Okay? And then the last thing in chapter 5 your book goes into is something known as the field concept. So far we've assumed that the force between two masses is the result of some type of direct interaction, basically an action at a distance interaction. Now, that could be a little unsettling because there's no direct pushing or pulling in that intervening space. We do know that gravitational effects are evident when there's a vacuum between the masses. And what we do, we conceptually and we computationally separate the gravitational interaction into two distinct steps using the field concept. The first step is one of the objects is going to modify, by virtue of its mass, the surrounding space. So it's going to produce a gravitational field at every point in space. Secondly, the other object's going to interact by virtue of its mass with that gravitational field to experience a force. So basically, we are going to take the field concept, we're going to divide the task of determining the force on a mass in two parts. First, we're going to determine the field from the first mass, and then secondly, we're going to calculate the force that the field exerts on the second. If this was the whole point of the field concept, it would be a very minor role in physics, because it kind of seems like we're trading one unsettling idea for the next. But as we continue to go on, you will see how the field concept becomes very important to us. Okay, this ends chapter 5.